Okay, so now that we have replaced the derivatives with the finite differences here, we are going to simply plug in numbers and just try to see how the calculations proceed in a finite difference method.
So the heat equation del T equal to alpha del square T del x square, we have converted it to an algebraic equation T at I at j plus 1 is equal to T I j plus alpha del T over del x square times T at I plus 1 j minus 2 ti j plus ti minus 1 j. So I rewrote the equation that we just derived. So this one has been converted to this one, and then let's just relate this ij. So I stands for these points. So back to our problem. Remember, this is the problem we're trying to solve for a slab. So this in the slab, we're not solving for everywhere. We're not solving for the entire thickness. Instead, we have these points. So I is this 1, 2, 3, 4, 5. I equals 1 through 5. Those are the locations that we are going to solve. And we start from some initial temperature, and then we are going to solve these values, and so let's see how that does that go. So at j equal to 0, I have these temperatures: temperature at 1 at time 0, temperature at 2 at time 0, temperature at 3 time 0, temperature at 4 at time 0. So those really are, time 0 is my initial condition. We cannot do this problem. We cannot calculate temperature next time if we don't know where we are starting from. So these are my initial temperature. So at a time j, at a time, or using this equation recursively, T I at 1 is equal to Ti at 0 plus alpha delta T over delta x squared times T at I plus 1, 0 minus 2 Ti 0 plus Ti minus 1, 0. Okay. In other words, if we know all the temperatures at time 0, we can find temperature at some point at time 1. So that's what is shown here, is these guys are all known, and now I'm going to use this equation recursively. So if I put I equal to 1, then I get T1 1 is equal to T1 0. Okay, but if you do this, you notice that you get T of 0, but there is no location at 0. So putting I equal to 1 is not a good idea. We don't need to. So I basically does not vary from 1. So instead of that, we can put I equal to 2. So I get T2 at 1 is equal to T2 at 0. Let me clean this up. T2 at 0 plus alpha delta T over delta x squared times T3 at 0 minus T2 at 0 plus T1 at 0. So you notice the interesting part. Everything that has a subscript 0 is known. Okay? And so we can calculate from this the T2 at 1. So how do I get T1 at 1? So notice T1 is here, that's boundary. So that comes from boundary condition. And we'll do the details later, or you can look into any of the reference books. And then likewise, this T5 also is related to the boundary condition. So that's the additional information that we need. So with that, we can solve for all the interior points, and then we just repeat this entire process to get to the next one. And we keep going. So that is called marching in time. So we now have these temperatures at the discrete locations at any time, and using those values at one time, I can calculate at a later time what are the values at the same place. So we have now discretized, and we're able to solve the heat equation without really going through the details that we do in our partial differential equations class. So this is using the numerical solution. Okay, now we will plug in numbers into what we just derived. So let me just repeat the equation that we wrote in the last slide. So T21, so calculating temperature at node 2 is given by alpha delta T over delta X square times T 3 0 minus 2 T2 0 plus T1 0. Okay, and now we can plug in numbers. So basically anything that has a 0 subscript, that is the initial condition. So the initial node, like these guys, they are given. So this is my initial node temperature. So all the zeros are known, and so I can just plug them in. And I happen to choose delta T equal to half a second, and then some value of delta X that also we chose. And with that choice, I can calculate the new value here. So what are we doing in this figure here? We know the initial values. So at all the points, initial values are known, and then T21 is this guy. So I am calculating this guy. Except for the numbers given, we're actually doing a cooling problem. So this is like the new surface temperature, and my temperature, the new temperature calculated at T21 is somewhere here. Okay, so similarly I can write an equation for T3. So T31 is equal to T30 plus alpha delta T over delta X square times T40 minus 2T30 plus T20. So all of these guys are known, so I can find T31. In this case, because these guys are all zeros, then T31 does not change. Okay, so similarly T4 also would not change. So what about T5? So T5 is this point. So this is obtained using boundary condition. So what is my boundary condition here? So the boundary condition at this is del t del x at the location 5, at location 5 is equal to 0. So I can write the derivative at location 5 as t4 or t5 minus t4 equal to 0, divided by delta x equal to 0. So that means t5 is equal to t4. So once we have calculated t4, we can set t5 is equal to that. So notice how we got this point. This was using boundary condition, and the same way here, this value is set as boundary condition. So these two are given, and then we calculated the one in between. And so we can now progress to the next time step, and that's going to look something like, let's say this one at the next time step is going to be t2 at 2 is equal to t2 at 1 plus alpha delta t over delta x squared times t3 at 1 minus t2t 2 at 1 plus t1 at 1. Okay, so t2 at the second time step is calculated from all these values that are at 1, but they are all known now, so I can calculate this value. And so we repeat this process at the next time step and next time step and so on. That's why this is called marching in time. So the finite difference equation is written again here, just repeated, and not written in terms of I and j, but x and t, but it's the same equation. The only point being made here is, so suppose I have 3 nodes, and so I write this equation uh, for these 3 nodes, and so you'll get 3 equations, and here this just writes it in the matrix form. Okay, so on the right hand side, this matrix is all known because these are the values at the previous time step, just like here. So this is t plus delta t is the new time, and this is the old time. So all the old time step values are here, and this is the inside all of these elements. They are known from what we chose as alpha and delta t and delta x squared. Okay, so then finally we can write this thing for all the elements, and it's going to look something like this one. And the point is, the very last ones are dictated by the boundary condition, and this is all known stuff. So at the end, then the matrix looks something like this. The entire set of equations look like this. T at j plus 1, t at new time step, you can solve in terms of old time step. But I want you to see the big picture. So we didn't solve the partial differential equations analytically. We are able to solve it following this method without going through any of the techniques, like how we did a series solution of the equation. We didn't do that. So this is the alternate way of solving the same equation, and it has the flexibility, because you see, I do not need to know any special technique for solving the original equation, like the series solution. I could just write them in terms of finite difference and then just solve that equation, and then I will be done. But notice that I am solving at distinct nodes. I'm not solving everywhere. So that's because I'm not solving it analytically. I'm solving it in discrete at discrete locations.